between energy exchange and hybrid electrical cells?
Thank you. First of all, I would like to express my deep gratitude to organizers of program and to all participants in this room. Theme of my talk is photorefractive effect and two-beam energy exchange in hybrid liquid crystal cells. It's joint work with my colleagues Viktor Reshetnyak, Tim Slutsky, Gary Cook, and Dean Evans. I would like to say a few words about photorefractive effect in general. Photorefractive effect is a phenomenon in which local index of refraction is changed in response to illumination by light with spatially varying intensity. Such effect was first observed in early 16th. There are several stages in this effect. A photorefractive material is illuminated by coherent light beams. Interference of the beams results in a pattern of dark and light fringes throughout the crystal. In bright regions, electrons can absorb the light and be photoexcited from an impurity level into the conduction band, leaving an electron hole. Once in the conduction band, electrons diffuse towards the dark fringe regions. Here they fall into the traps. The redistribution of electrons into the dark regions of the material and holes in the bright areas causes a spatially periodic electric field, known as a space charge field. The space charge field, via the electro-optic effect, changes the local refractive index of crystal and creates a refractive index grating. The refractive index grating can now diffract light, and as a result, energy exchange between beams at the grating is possible. Here's a picture for charge redistribution. Electrons move to the dark regions and fall into the traps. Holes live in the bright regions. And we have charge redistributions, which creates space charge field. Space charge field causes refractive index grating. We will study energy gain in system of two coherent beams propagating a medium with refractive index grating. There is interaction between beams at the grating, and as a result, amplitude of one of the beams, signal beam, increases or decreases. General parameters which characterize the gain is ratio amplitude of signal beam at the exit to amplitude of signal beam at the entrance. Or we use more often the exponential gain coefficient determined by this formula. Now about effect in our system. Two interfering light beams intersect and produce in photorefractive inorganic materials, named as photorefractive windows, a space charge field, which penetrates into a bulk of liquid crystal. Interaction between the director and the photorefractive space charge field induce a periodic modulation of the director. Periodic director modulation gives rise to the refractive index grating, because the electric function of the liquid crystals depends on the director. Then each light beam diffracts from the induced grating, leading to the energy gain and loss within each beam. Here is a scheme of our system. We have inorganic photorefractive crystals and liquid crystals between them. Two beams, strong pump beams and small signal beams, creates interference pattern in the inorganic photorefractive crystals. And here we have space charge field only in inorganic photorefractive crystals. Space charge field penetrates into liquid crystal and change the director and write the director grating and refractive index grating. Comparing with results in different schemes. In solid inorganic photorefractive crystals, gain coefficient reaches 10 or 100 inverse centimeters. In like photorefractive liquid crystals, when space charge field arises in liquid crystal due to space separation of photogenerated negative and positive ions, gain coefficient reaches value 3000 inverse centimeters. Nematic liquid crystal can be reoriented, but photogenerated space charges in adjacent polymer photorefractive or photoconducting layers. And we have such gain coefficient. This case is similar to this, but instead of inorganic photorefractive crystals, there are polymer substrates here. But gain coefficient reaches this value. Some addition. Tubing coupling is these devices is restricted to operation in the Raman-Nath regime. In this regime, multiple order diffracted beams are generated. To minimize this effect, the angle between the PAM and signal beams is restricted to less than a few degrees. Thus, the effect might only be of limited technological applicability. In our system, in hybrid liquid crystal inorganic photorefractive crystals, gain coefficient exceeds 600 inverse centimeters. But system supports the Bragg regime when only first order diffracted beams are generated. And some explanation of this. Inorganic photorefractive crystals, substrates of liquid crystal, typically have a large effective trap density. Thus, the small trap density in liquid crystals or in polymers is complemented by the large trap density in inorganic photorefractive windows. It allows supporting efficient space charge field generation at small grating spacing required to reach the Bragg regime, big angles between two intersecting beams. A few words about Bragg regime and Raman-Nath regime. Usually, it is possible to distinguish two extreme regimes, Raman-Nath regime and Bragg regime, or thin gratings and thick gratings. Bragg regime, as was mentioned before, is characterized by observation of single diffracted order for each incident beam. In the Raman-Nath regime, multiple diffracted orders are observed. Distinguishing between the two regimes is not necessarily straightforward, as diffracted beams may be reflected inside the medium. The most common method to distinguish between the two regimes is to define the dimensionless parameter, plane parameter. Here is grating spacing, wavelengths, homogeneous path of refractive index, thickness of the medium. The Bragg regime is then defined as Q much more than 1, and Raman-Nath regime as Q much less than 1. In the case of Raman-Nath regime, we consider a medium with periodic modulation, with periodic modulated refractive index. And the interaction L is small enough that the medium acts as phase grating. If the incident at the angle theta, the plane wave, is as here, the time-independent part of wave at far side of the medium can be expressed in this form. It's simply to substitute x instead n this value, here. But using the famous formula, we can present wave at the far side of the medium in this form. So we have many diffracted beams, Intensity of each of the diffracted beams is definite as square of the amplitude. Intensity. In the case of Bragg diffraction, we substitute the periodical modulated dielectric function into the wave equation. It's assumed that the medium is thick, and as such, any higher diffracted orders, besides first order, will be attenuated as they propagate. Then, using method of slowly varying wave amplitudes, we get system of two couplet equations for amplitudes of diffracted and non-diffracted beams. In photorefractive medium, the diffraction gradient is induced by two intersecting interfering light beams. Gradient wave number is determined by the angle of intersection. In this case, the diffracted beams are automatically superimposed on non-diffracted beams. As a result, in photorefractive medium, in the Bragg regime, we have system of only two couplet equations for amplitudes of two propagating waves. Here's a picture which explains the Bragg regime and Raman-Nath regime. Thick gradients, thin gradients, many diffracted beams. What we will study? We will study energy exchange between light beams on the director gradient in hybrid liquid crystals in organic photorefractive cells, and develop theory to describe experimental results. Experiments give us a small signal gauge coefficient as a function of gradient spacing in the liquid crystal cell. Here is experimental results. Here is nematic liquid crystals between photorefractive substrates. Here is gain, not gauge coefficient, only gain. And here is gradient spacing in micrometers. There are curves for cells of different thickness, 10 micrometers, 20 micrometers, and 38 micrometers. Another case, when between photorefractive windows, we have holosteric liquid crystal. Here we have holosteric liquid crystals. Here is gain coefficient, gradient spacing. Different holosteric liquid crystals. Holosteric liquid crystals are obtained adding to nematic host, Bl, TL, chiral agents, CB15. And we have different dependence of gain on gradient spacing. Here we have this for nematic and for holosteric. Our modeling strategy of our theory, we determine electric field profile within photorefractive substrates, then electric field profile in liquid crystal cell using periodic electric potential of photorefractive substrates as boundary conditions for this field. Then we seek director profile in liquid crystal cell subject to spatially periodic electric field, describe light beams interaction on director gradient using couplet wave theory, and finally calculate signal beam exponential gauge coefficient depending on parameters of gradient and cell. Electric field in photorefractive substrate. Light intensity interference pattern where modulation parameter contains amplitudes and intensities of incident beams. Within the photorefractive layers, light intensity pattern induces the space charge, which creates a space charge electric field, modulated along x-axis along x-axis with period equal to 2 pi divided by q. The space charge field creates electric potential at the LC cell, also spatially periodic. The magnitude of electric field potential can be estimated using this formula. Here is modulation parameter, which contains amplitudes and intensity of beams at substrates, top and down substrates. It's concentration of acceptors in photorefractive substrates. It's concentration of donors. Now we consider the case when nematic liquid crystal is between photorefractive substrates. So we seek electric field inside nematic liquid crystal, solving Laplace equation. Here is flexopolarization, and electric field inside nematic LC obtained approximately from this equation. Then we seek director profile in liquid crystal by minimizing the total free energy functional of the liquid sample. Bulk elastic energy, light field contribution, DC electric field contribution, flexoelectric polarization contribution, and the sophistem. We will neglect light field contribution due to the small dielectric anisotropy at optical frequencies. And suppose strong anchoring in some easy axis directions at the cell walls. Instead of the sophistem, we will use absolutely rigid conditions for director at the cell substrate. So we have terms: bulk elastic, DC electric field contribution, and flexoelectric polarization contribution. Now we make some estimates. We have cell thickness, great innovative wave vector, elastic constant, dielectric anisotropy, static dielectric anisotropy, flexoelectric modulus, and we can estimate elastic energy density for this wave number, space charge field, flexoelectric temp contributions into total energy, and as a result, we can find ratio of anisotropic part of the liquid crystal electrostatic energy density to elastic energy, and find ratio of flexoelectric energy density to the elastic energy density. We can see that this ratio is much more than this ratio. So we can neglect term Fe in the free energy of the liquid crystal. Here, we can neglect this term too. And the main terms are elastic term and the flexoelectric polarization term. Two terms are main in the total free energy functional of the liquid crystal sample. It's convenient to describe director profile as this. Minimizing basic solution to the equation in such form and minimizing the total free energy functional, we get equation for theta and for theta 0. It's equation for theta and it's solution for theta 0. Analytical solution to theta also exists, but it is cumbersome and I omitted it here. Its example, magnitude of periodic part of liquid crystal director profile. Angle theta, its distance between substrates, coordinate z, and for different gradient spacing. The longer grating spacing, the higher director distortion, and wider distorted area of the liquid crystal. We have director distribution in liquid crystal cell, and now we can consider propagation of light beams across the cell. In our case, Klein parameter much more than one, so we have C grating, and they are in Bragg regime. The electric tensor at optical frequency has the form, has periodic path. Here is path. Describe homogeneous liquid crystals with constant angle equal director pre-tilt. Sorry. Epsilon t is contribution due to inhomogeneity of director distribution produced by director pre-tilt at the cell substrates. And finally, epsilon 3 contribution from director grating. Its contribution from director grating contains angles theta and theta 0, which were determined before. Basic solution of the wave equation with this dielectric tensor. Sixth solution in this form, where amplitudes of one beam and the second beam are slowly varying functions. After some algebra, we get couplet wave equations for wave amplitudes. Taking beam 1 to be a weak signal and beam 2 to be a strong pump beam, these equations in these approximations reduce to single equation. There is analytical solution to this equation. So we have amplitudes A1 and A2. Having amplitudes A1 and A2, we can calculate the gain coefficient. We can see the gain coefficient is proportional to the space charge field and the flexoelectric parameters. We calculate this gain coefficient. Here is parameters for calculations, typical parameters for pneumatic liquid crystals TL, light, wavelengths of light, refractive index of ordinary wave or extraordinary wave. It's for photorefractive beam, for photorefractive substrates, low frequency dielectric constants, and ratio, this typical have order of 1. Cell thickness, 10 micrometers, grated spacing, 1.6 micrometers. Comparison with experiment. Here is experimental data, and here is theoretical results. Here is log of gain coefficient and grating spacing. We can see the agreement is poor. To solve this problem, we carried out additional experiments with third beam. Idea of the experiment is to check the law of the gain coefficient dependence in the hybrid cell on the space charge field. Adding the third beam of different wavelengths decreases the space charge field. We have pump beam, signal beam, and we now added the third beam with different wavelengths. And then space charge field due to this third beam changes its value. Intensity of beams increases, space charge field decreases. So we can measure gain coefficient as function of the space charge field. Conclusion from results of experiment with the third beam: gain coefficient depends on space charge field non-linearly as third power. Probably because of this. Liquid crystal is a mixture. It's plausible that one component has a higher permanent dipoles, which determines the Flexner coefficient value. The inhomogeneous space charge field may cause liquid crystal mixture molecules with different dipoles to separate. The result of separation is a special inhomogeneity of Flexner coefficient, which depend on space charge field. According to the results of experiments with the third beam, we now replace flexoelectric coefficient, which is constant, but flexoelectric coefficient which contains space charge field in square. And compare the results of theory with experiments. Here is comparison with experiments. We have different cell thickness, gain coefficient for cells of different thickness, gradient spacing, curves theory. Theoretical fitting with experimental data assumes that we have, instead of constant flexoelectric coefficient, this value containing space charge field in square. Mu is fitting parameters, only one fitting parameters. It seems that correspondence between the modeling and experiment is now quite good. Now we consider holosteric liquid crystals between photorefractive substrates. Holosteric, which we obtain adding chiral agents to a pneumatic host. Preliminary estimates. We would like to find the director and chiral dopant profile when there is non-zero director pre-tilt at the cell substrates. Then we must minimize free energy functional. Electric field is absent here. Here is entropy term, and constrains this strong anchoring of the cell cells. F is volume fraction of the chiral agent. C is solute concentration, characteristic volume. If there is no initial pre-tilt, then solution for this is holosteric liquid crystal with homogeneous helix. Concentration of chiral agents is constant. Helical wave number proportional to the concentration is also constant. So we have homogeneous helix in liquid crystal. But if we have initial director pre-tilt and the cell substrates, we can suppose then chiral molecules to be homogeneously distributed in the LC host. The Euler-Lagrange equation we obtained by minimizing the free energy functional has this form and can be numerically calculated. Here's numerical solution only for chiral agent profile. Here's distance between substrates, and here is concentration of chiral agent. Case for initial non-zero pre-tilt of 15 degrees. We can see that near the substrates, chiral concentration is smaller than in the middle of the cell. Then we seek the equilibrium director profile by minimizing the total free energy now for holosteric sample, bulk elastic energy, only flexoelectric polarization, and entropy contribution. But to simplify calculation, we assume that directa near the cell surfaces, where the concentration of chiral agents is small, we assume the directa ordering to be nematic. While in the central part of the cell, there is a holesteric ordering with some constant pitch of holesteric helix. We also suppose strong anchoring as the cell substrates. Thickness of these nematic layers near the cell substrates is the fitting parameter. Then we seek directa profile as for nematic LC. We seek electric field from Laplace equation, then substitute an electric field in the equation for directa angles in nematic and holesteric layers of liquid crystal. We get an analytical expression for directa spatial distribution. There is no experimental evidence that the holesteric pitch changes under photorefractive field. Therefore, we can suppose that photorefractive electric field does not influence the holesteric pitch. Then we can put the azimuth angle of holesteric does not change under the electric field, and described by this famous formula. And the directa gradient is now written only on the polar angle. Preliminary estimates for these holesteric liquid crystals, refractive indexes of ordinary wave, extraordinary wave, pitch. Since these conditions is fulfilling, we are in the regime when one incident beams produces in holesteric two secular polarized light waves. One light wave is polarized to right and another to left. Secular polarized two waves. Refractive indices difference for left and right polarized waves is small. Small is rotation of beam polarization through the cell. It agrees well with experimental result, then transmitted optical polarization remains linear at the exit of the holesteric layer. So, we can conclude that in our case, the light waves maintain the linear polarization, even within that part of liquid crystal cell, which is specifically holesteric. Therefore, we can simplify the optical part of our considering only two linearly polarized beams instead of four secularly polarized. Then we solve Couplet equation for these two linearly polarized light beams, and finally calculate small beam gain coefficient. Comparison with experiment. 5 micrometers cells for two different holesteric mixtures. Goes theoretical results. As enigmatic liquid crystals, flexoelectric moduli is replaced by the value containing the space charge field in square. Fitting parameters here. There are 3 fitting parameters. Mu, ratio, thickness of the layer with nematic ordering. It's too small. 3 micrometers, graded spacing. 3 micrometers. Comparison with another experiment for thicker cell, for cell of thickness 10 micrometers. It's also maybe considered as good. Why so different is behavior of gain coefficient in nematic and holesteric liquid crystal hybrid cells? Answer is simple. There is different character of directa deviations under photorefractive space charge shield. In nematic LC, directa deviations are governed by single flexoelectric parameters. But in holesteric, by two flexoelectric parameters, and one of them is negative. So this deep negative value is connected with influence of deviations of director, which are governing by these flexoelectric parameters. Conclusions. Flexoelectric polarization is the main physical mechanism governing the magnitude of the LC grating, and hence of the two-beam coupling in hybrid photorefractive cells. Experimental data of the gain coefficient in hybrid cell filled with LC mixture TL show that the magnitude of the director grating is a nonlinear function of the space charge field. The microscopic origin of the nonlinearity is at present not entirely clear, but the most hopeful possibility focuses on the fact that the liquid crystal is not a pure system, but a mixture. The inhomogeneous photorefractive space charge field within the liquid crystals induces chemical moiety inhomogeneities, which interact with flexoelectricity to produce a nonlinear response. We find that a fit between the experiments and theory can be achieved. We believe that the fit provides good evidence that the K-physics of this system has been correctly identified. Future work. When light beam's way appears in holosteric gamma, and we have essential rotation of the light beam polarization. Thank you very much.
Well, you need the thickness of pneumatic as a fitting parameter. You could find it from minimization, like depletion.
Yes, but the thickness of pneumatic layer is a fitting parameter because in the middle of the cell we have holosteric.
Yeah.
What is the thickness of this layer, pneumatic layer? We don't know. It's
not the same as you shown on depletion concentration of.
Yes, it is connected with a depletion of the concentration. But I would like to explain. Just a minute. This here is for holosteric. This layer, it's necessary for us to explain positive part of this gain coefficient. If we have purely holosteric liquid crystals, we have only negative gain coefficient and a high grating spacing. So we must use this pneumatic layer to explain here. But his thickness is fitting parameter. We cannot.
When you determine this new parameter, this electric separation parameter, depending on E squared, it should actually be then essentially dependent on the different polarizabilities of individual molecules. So now you have the fitting parameter, and you can get some estimate from the known dielectric constant of the two species in your. Does that give you a correct sort of?
I can suppose there is a connection. There is connect with them, but we don't study this connection. So it's fitting parameters. I understand that it connected with dielectric values. So we must measure dielectric constant, which is now specially inhomogeneous.
Okay, but this would be difficult. But you know your components, and the dielectric constant of each individual component should give you at least an estimate for the mu.
Maybe, but I didn't know these values for these components for BL and CB.
You can say, I mean, one can be, let's say, 1 and the other can be 10. What would that give you for mu?
Maybe. I agree. We can be.
How do you calculate the space charge field?
We used the formulas which we not derived, but take from the books. It's a book of Ye, it's theory of Kukhtarev. She derived the formulas for space charge field in solid photorefractive crystals. And we use these formulas, they not exactly good for our case, but as order of value, we can use it.
We have flexoelectric fields present as well,
Yeah.
which presumably have an effect on the charge behavior, which gives rise to the field. So, I mean, I could see that this should be maybe done self-consistently, unless you can show that the effect is negligible.
I didn't understand your question to the end, but I would like to explain to not understand it. Flexoelectric polarization is liquid crystals appears here only as interacted with space charge field which penetrate from inorganic photorefractive crystals. We have no space charge field into liquid crystals. Space charge field creates in inorganic crystals and penetrate. Liquid crystal does not create space charge field, but it can be. But it can be. Thank you very much for listening to me.